Hello and welcome everyone to the Agentic AI Developer Bootcamp. Before we dive into the hands-on demo, we are going to spend a few minutes on the theory part because if you understand why RAG works the way it does, the code you write in the next few minutes will make a lot more sense. Today's session is focused on RAG, Retrieval-Augmented Generation. We are going to build a compliance chatbot on top of the Basel III regulatory document using LangChain, FAISS, and OpenAI's GPT-4o. So if you have any questions at any point, feel free to drop them in the chat or raise your hand. Let's get started. Moving to the next slide, uh, which starts with the question, why can't we just ask ChatGPT? So the very first question people usually ask is, why can't we just type our question into ChatGPT and be done with it? It's a fair question. The answer comes down to three fundamental limitations of standard large language models. The first one is hallucination. The LLMs are trained to generate fluent, confident text, but they don't always generate correct text. They can fabricate facts, cite non existent regulations, and give you a wrong answer with complete confidence. In a consumer app, that's annoying. In a BFSI compliance context, that's a regulatory risk. Second is knowledge cutoff. So the current GPT model's training data ends at a certain point in time. Okay, so it's not up to date. It's not keeping updated with the present date. So any RBI circular issued last month, any SEBI amendment from this quarter, the model simply doesn't know about it. It can't tell you what it doesn't know. The third and most importantly for our use case, which is private data. Your internal policy documents, your Basel III supplements, your firm's interpretation of SEBI guidelines, that's a data the model has never seen and possibly never will, unless you give it to the model at the query time. So that's exactly the problem RAG is trying to solve. The next part is RAG stands for Retrieval Augmented Generation. Okay, the simplest way I can describe it is RAG gives the LLM the answer sheet before the exam. So instead of asking the model to rely on its training data, we do three things. Step one is retrieve. We take the user's question and search our document library for the most relevant chunks of text. Not keyword search, which is semantic similarity search, which we'll explain shortly. Step two is augment. We take those retrieved chunks and add them directly into the prompt we send to the LLM. The model now has the relevant context right in front of it. The third step is generate. The LLM answers the question using only what we gave it. So there is no outside knowledge. So it's grounded in its local source. So it's grounded, cited, and it is auditable. So this approach was first introduced by Lewis in 2020 at Facebook AI Research, and it's now the industry standard for any AI application that needs to be grounded in specific trusted documents. Let's take a look at the RAG pipeline end to end. Let's look at it from start to finish. There are two distinct phases. The first is the indexing phase. So this runs once when you set up the system. You take your source document, in our case, it's the Basel III PDF from the BIS website. You load it, split it into chunks, convert each chunk into a vector embedding, and store those vectors in a FAISS index. So this is your knowledge base. You build it once. The second is the query phase. This runs in real time. Every single time a user asks a question, the user's question is converted into a vector embedding. That vector is compared against all the vectors in FAISS. The top four most relevant and diverse chunks are retrieved, and those chunks are stuffed into a prompt that goes to the GPT model. the GPT reads the context and generates a grounded, cited answer. Now, you can think of indexing as building a real smart search index, and the query phase as actually using that index to answer questions. Moving to the next slide, where we will describe the all relevant steps, starting with step one, which is loading source documents. So let's walk through each step in detail. The first is document loading. So here we will be using the PyPDF loader from LangChain to load the Basel III PDF. You give it either a local file path or a direct URL. In our case, we are pulling directly from the BIS website. The PyPDF loader downloads and passes the PDF page by page using the PyPDF library under the hood. It returns a list of document objects, one per page. Each document has two things: the raw text content of that page and metadata, including the source URL and the page number. Then, why does the page number matter here? Because when GPT gives an answer, we can tell the user exactly which page of the PDF it came from. Okay, so there is full traceability. And here's the best part. This loader is completely document agnostic. So you swap the BIS URL for an RBI master circular, a SEBI guideline, an IRDI policy. The rest of the code doesn't change at all. Okay, let's move to the step two, which is why we chunk documents. So the step two is the chunking part. And this is where a lot of people initially ask, why bother? The answer is simple. LLMs have a context window limit. You cannot feed a 70-page PDF into a single prompt. So you have to select the most relevant sections. And to select the sections, you first need to break the document into retrievable pieces. So here we use recursive character text splitter. So the key parameters are chunk size of, let's say, 800 characters, that's roughly 200 tokens, and chunk overlap of 150 characters. The overlap means the last 150 characters of one chunk become the first 150 characters of the next chunk. So this prevents the situation where an important sentence gets split right across a boundary and loses its context. Then the splitter tries to split at natural breaks in this order: paragraph breaks first, then line breaks, then spaces, and only as a last resort does it cut mid-word. Okay. The result is our 69-page Basel III PDF becomes roughly 500 overlapping chunks. And each chunk is one independently retrievable unit in the FAISS index. Okay. Moving to step three. Step three is where the magic really happens, where you're turning text into meaning through embeddings. An embedding is a list of numbers, a vector, that captures the semantic meaning of a piece of text. Not the exact words, but the meaning. And here's the key insight that makes RAG so powerful. The phrase capital buffer requirement and the phrase reserve cushion mandate use completely different words. So a keyword search would treat these as unrelated, but their embeddings, their semantic vectors are very similar because they mean the same thing. So we are using OpenAI's text embedding 3 small model. It takes any chunk of text and returns a 1536 dimensional vector. You can think of it as a point in 1536 dimensional space where similar meanings cluster together. So when we later search for relevant chunks, we are measuring the cosine similarity between vectors. So a similarity of 1 means identical meaning. A similarity close to 0 means unrelated. So this is why RAG retrieves relevant content even when the user doesn't use the exact same terminology as the source document. Moving to step 4, which is the vector store, which is the semantic search engine. So it's the step 4 is indexing all those vectors into FAISS, which stands for Facebook AI Similarity Search, needless to say, developed by Meta Group. So FAISS is a library optimized for extremely fast nearest neighbor lookup across millions of vectors. So when you ask a question, FAISS finds the vectors closest to your question's vector in a fraction of a second. To make this concrete, compare it to traditional keyword search. So if a user types LCR, keyword search only finds documents that literally contain the letters LCR. So FAISS semantic search finds documents about liquidity coverage ratios, even if they never use the acronym. We also use a retrieval strategy called MMR, maximum marginal relevance. So standard top K retrieval just returns the 4 most similar chunks, but these are often near duplicates of the same paragraph. So MMR balances relevance and diversity, so you get broader coverage of the document, giving the GPT model a richer, more varied context to reason from. Uh, One last note is FAISS is perfect for local development and demos. In production, you will swap it for a managed vector database like Pinecone, VV8, etc. But the rest of the pipeline stays identical. Next, we move to the step 5, which is the LangChain LCEL pipeline. So step 5 is where we assemble everything into a single pipeline using LangChain's LCEL, LangChain Expression Language. LCL lets you chain AI components together using the pipe operator, just like Unix pipes. So each component is a runnable uh, and you chain them left to right. So our pipeline works like this. The user's question goes into a runnable parallel block that simultaneously calls the retriever, which hits FAISS and returns the top chunks and passes the question through unchanged. Okay. The retrieved documents get formatted into a clean text block by format docs. That context and question are inserted into the chat prompt template. That prompt goes to GPT model with temperature set to 0. Okay. And the output is passed from an AI message uh, object into a plain string. Here, temperature 0 is a critical choice. It means the model is fully deterministic. So there is no creativity, no randomness in the response we want. The same question will give the same answer every time, okay, which is what we want in this particular case. In a compliance context, you want that predictability. And the system prompt explicitly tells GPT, use only the context provided. Do not use outside knowledge. Okay, that single instruction is what prevents hallucination. So then we have the critical demo, which is RAG versus hallucination. And this is, you can say it's the most important slide in the whole presentation. In our demo, we ask 5 Basel III compliance questions, but the fifth question is deliberately out of scope. We ask what is the current repo rate set by the RBI, and the Basel III PDF contains absolutely no information about RBI repo rates. So the base LLM, in which in this case is GPT-4o with no RAG, confidently answers the RBI repo rate is currently 6.5% as of February 2024. So it sounds authoritative, it sounds correct. It is completely fabricated though. Okay, this is hallucination. The model made up an answer because it was trained to always produce a response. Our RAG pipeline says I don't have that information in the provided document. Please refer to the full BIS Basel III publication at bis.org for further guidance, which is clean, honest, and auditable. So this is the difference between a useful AI tool and a liability. In compliance, auditability matters as much as accuracy, and RAG delivers both. Next slide is why RAG is transformative for BFSI. So let's talk about what this means for different roles in a BFSI organization. For compliance officers, instead of manually searching through hundreds of pages of Basel III, RBI circulars, and SEBI guidance, you get instant cited answers. Every response links back to the source. For risk managers, you can ask grounded questions about leverage ratios, LCR, NSFR, and capital buffers and get answers where every number is traceable to a specific section of the source document. Then for the auditors, this is potentially transformative. So if every RAG answer includes the exact source chunks used to generate it, so you have the full audit trail and zero hallucination and 100 explainable and something which is 100% explainable to a regulator. Then for the leadership, the pipeline scales. You don't retrain any model, you just add more documents to the index. So RBI master circulars, IRDI regulation, SEBI, internal policy manuals, the same pipeline handles all of it. So this is why RAG has become the go-to architecture for enterprise AI in regulated industries. The next is what we are building in the hands-on session. So let's talk about what we are about to build in the next one. We have 7 steps. In the first few minutes, you'll install dependencies and set up your OpenAI API. In the next part, you'll load the Basel III PDF directly from the BIS website using PyPDF loader. Then we chunk it, splitting 69 pages into roughly 500 overlapping chunks. In step 4, we create the embeddings and build the FAISS index. This is where your documents become semantically searchable. Step 5 is assembling the LCL chain. And in step 6, you will run 5 pre-written Basel III compliance questions, including the hallucination test we just saw on the previous slide. Step 7 is the live demo is completely open. You can ask any Basel III question you want in real time, and we'll see the system answer it live. By the end of the session, you will have a working compliance chatbot running on a real regulatory document, which will live in your Jupyter notebook. And it's not a toy, it's a real production pattern RAG pipeline. Now, at the end, the key concepts to remember. So before we open the notebooks, let's do a quick recap of the 5 components that make up the RAG pipeline. Starting with the PyPDF loader, which will load any PDF, whether it's a URL or a local file, and returns document objects with source and page metadata. Second is the recursive character text splitter. It breaks those documents into overlapping retrievable chunks with a chunk size of 800 characters and an overlap of 150. Next, we have the text embedding 3 small, which is the OpenAI model that converts each text chunk into a 1536 dimensional semantic vector. Then we have the FAISS plus MMR, which indexes those vectors and retrieves the top 4 diverse relevant chunks for every query using maximum marginal relevance. And then we have the LCEL pipeline, the LangChain chain that wires retriever, prompt, the model, and the output parser together with the pipe operator. So remember the formula: RAG equals your documents plus your semantic search plus your LLM reasoning equals grounded auditable AI answers. So with that, we can end the presentation.